subgradient, you have lots of derivatives, blah blah blah. These are if f is general. General in the sense that it's nonlinear or some other crazy thing non-convex, but if all of them are convex, magically they all reduce to this one. Differential, convex, subdifferential. What's the convex function? You have something below you. This is subdifferential. Why? Because this straight line have a normal. It's subdifferential. Actually, this normal is not subdifferential. This normal, removing the last coordinate, is the subdifferential. I will talk about this today. So basically, that is what's this convex function? Okay, this is convex function, right? Because I have a point here, I draw a line. This line is below the whole graph, and this is true for any point. This is the idea of convex set, right? Because epigraph. So line is got support below the epigraph. This line have a slope. The slope of this line is the slope of this function at this point. And if function is differentiable, we only have one slope. But if the function is not differentiable, we have more than one. That's it. So what are the examples of non-differentiable but convex function? Absolute value. This is one example. L1 norm, nuclear norm, the sum of singular value. These are all convex, but not differentiable. There are other things that are the same. These are another example. I have a bunch of AX and then max them. This is also convex. What is this? This is something like this. The max of these two, this thing, green. Then in this general form, you can have something that looks like this. So this is convex set. Convex set, convex epigraph, so function is convex. So that's the idea. And then this is the same thing. Largest eigenvalue also convex. And then indicator function is also convex. And why? You can use epigraph. What's epigraph? Epigraph saying that if the function, I fill water on top, then I have a shape. This shape is a convex set, then the whole function is convex. I have infinitely many subgradients. Together it's called subdifferential. So that's why we have a set. So this G have more than one G, that this is true. And that G is exactly gradient. But if my function is not differentiable, I have more than one G. And this G actually includes the normal gradient. 0, right? So the slope is 0. So what will be the largest possible slope here? A line that is exactly touching the blue. So the slope of the green is exactly the slope of the blue here. What's the slope of the blue here? 1. So the largest slope is this green line. The slope is 1. What's the smallest slope? Not 0, it's -1. Because the smallest slope is this line, that the slope is the blue. The slope at this point is -1. So therefore, for this function, this is one-dimensional R1 to R1. So subgradient is also a one-dimensional number. So in this case, the G is just a number. It's somewhere between -1 and 1. And now this is funny. That means what? If I plot the slope, this is a slope. This absolute value is a f. This red thing is the derivative of absolute value in convex analysis. Why? Because in normal analysis, this is not allowed. Why? This is not a function. Why? 1x gives you more than 1y. You remember function is 1x go to 1y, and you cannot have 1x go to 2y. For example, a circle is not a function because at x equal to 3, you have 2 values. This is insane. At x equal to 0, you have infinitely many values. This is the set. At this point, 1x gives you infinitely many y. Any y between 1 and -1. Other than that, always either 1 or -1. This thing is the subderivative or subgradient or subdifferential of what f? Absolute value f. These two parts are easy, right? What about this part? This part is the complicated part. And in the classical sense, this part does not exist because the left limit, the limit of the slope is +1 approaching to 0. But here is -1. You cannot say -1 connect to +1. So here we allow more than one value and then suddenly we have something new. So what's subgradient? This is subgradient or subdifferential. Okay, here's the notation. This is not partial derivative. Okay, now this means subgradient. Okay, it's what? Define a supporting hyperplane. That means this free line to sub-level set through A. Okay, so what does it mean? Let's recap. What is level set? Level set is, or sub-level set, I have an alpha. It means any x that blue below green. So for alpha here, my sub-level set is this region. Okay, now if my alpha is exactly the value here, then of course my sub-level set is this point. So it's saying, what does it mean? It means red, this is red, this is red, to what? Green point, green point. So that means what? That means I'm saying, what is this alpha here? The arc mean of my f. Even though f is not differentiable, I can still talk about arc mean, right? That's the idea. So this is another idea. So I have this versus subgradient or subdifferential. Just this thing normally is a gradient. Now I said any g that this is true is a gradient. So this is generalization. So this g is not just one g, any g. Now this is what? Function description of this thing. What about if I do epigraph? Epigraph means what? I have epigraph f, so let's talk about this. So this whole thing is epigraph. Then what? Epigraph is two-dimensional object because epigraph is x coordinate and y coordinate. So now I have a coordinate in 2D. The x coordinate is x, y coordinate is f of x. So suppose my x is the minimum, then this will be the y coordinate of minimum. That means this point. So the x coordinate is the 0, y coordinate is also 0. Okay. Then what? This is a what? A coordinate. This thing, what is this? G-1 support epigraph at this. This epigraph is exactly the blue triangle. This thing, let me use yellow, is exactly this point, okay? Then what is this thing? This thing in red, what is G? I just told you G is -1 to 1. What is G -1? G -1, let me write it in vector form. What is this? It's saying all the x coordinate either -1 or 1 or something in between, but my y coordinate is always -1. Y coordinate is always -1 means I always point something like here. If G is +1, then I have here. This is a vector, so in the end the vector is this, right? If G is -1, my x point to here, and my vector point to this. What is these two arrows? These two arrows exactly this arrow and this arrow. So basically this arrow and this arrow is what? Is what I just said. The normal of this plane is this arrow. Or the normal of this plane is this arrow. And because G is anywhere between -1 and +1, so that means my x can be 1, -1, or slightly smaller, then this vector actually moves from here to here to here to here. So all my what? All my this is this triangle. What is this triangle? This arrow represents the normal to this hyperplane. This arrow represents the normal to this hyperplane. This arrow represents the normal to this hyperplane. Now you should see the idea. So in other words, I have something you have seen. I have a normal cone. This is the normal cone. What does it mean? Any arrow point into this triangle, the x coordinate is the subgradient. Let me give you another example. This is 0, and then suddenly this is x squared. Okay, suddenly this is x squared. Then what's the slope at this point? First of all, this slope, the smaller slope is what? The flattest one. Of course, it's this line. Then this line have a normal point to here. What about other slope? Well, I have a slope here, slope here, slope here, slope here. So for this funny example, first of all, actually, this is the only subgradient. Because actually this function is continuously differentiable here. So what is this? This actually is max 0x squared. Actually, this is continuously differentiable here. Then, now you see, if my function is continuously differentiable, first of all, this is still a convex function, but now my subgradient only have 1. Because I don't have this. Imagine, this means I have what? I have a slope that like this, but come on, this one will flat in the end at this point. So I only have one arrow pointing down. Yeah, that's the idea. So what about other idea? Okay, let me draw another idea. So suppose my function looks like this. Then, what is the subgradient here? Well, any 90 degree to this is the first one. And then this is the second one. So all the arrow will be this one to this one. What about this one? 90 degree here, 90 degree here. So these are 90 degree, okay? So it's this one. So let me use color. This one, the normal cone will be this. And this is the what? All the x coordinate at this point are the slope. All the x coordinate here at this point are the slope. All the x coordinate here are the slope. So now you have something more than classical gradient. Okay? So here's an example. Max. So what's the slope of max? Differentiable whenever x is larger than 0. Okay. Whenever x is smaller than 0, max of this is 0. So slope of 0 is 0. So for anything smaller than 0, the slope is 0. Okay. For anything strictly larger than 0, the slope is 1. Then what about at 0? Anything between 0 and 1. So this is the subgradient of this function. What is the normal cone? Again, 90 degree, right? This is to the blue line, okay, not the red line. And then here, 90 degree, okay. What is this shape? This shape is all the g coordinate, one is g, the subgradient, y coordinate is -1, so that's why it's pointing down. Supporting this point, what is the value of g? Either 0 or +1. So either you point 100% down or you point a little bit here until you reach the limit, that is 1. So yeah, correct. So all the arrow here, the x coordinate is the subgradient. If you understand this picture, you understand subgradient. That's it. Then what is the subgradient of L1 norm? Let's draw L1 norm. It's a diamond, right? It's a diamond. So it's something that looks like this. Okay? Okay, my drawing is very bad. So this is x coordinate, this is y coordinate. Okay? Then what is the subgradient at this point? It will be what? A hyperplane below this particular point, touching it, but everything on this plane is below this triangle, right? This is in 3D. Then the slope of this plane is a subgradient. And if I put the z coordinate, that means I extend the subgradient by one dimension, but always -1. Then I have something pointing downward. Then the collection of all these arrows of this kind of plane give me the normal cone. Then what will be the normal cone of this thing? It will be, okay, this needs some imagination, but it will be another cone like this, right? So all the cone, 90 degrees to all these 4 planes. That means I will have a plane that is like this. This is the first plane. That this plane and this plane have an angle. This angle is 90 degrees, right? Then all the collection of this thing, that means at most 90 degrees. Then I have a shape called a cone. Then all this arrow, that means I have an arrow here, I have an arrow here. Removing the last coordinate is the subgradient of this thing, which is exactly the slope of this plane. Then this will be what? The subgradient at this point. This is true for any function, as long as it's convex. You need to know, we don't talk about differentiability. We just said if this is true, then it's okay. And then what? Here's the first property. As I said, subgradient is a set. So is this set a convex set? The answer is yes. Subdifferential as a set is also a convex set. That means if G1 is a subgradient, G2 is a subgradient, then convex combination of G1 and G2 is also in subgradient. That's what we want to prove. First, G1 is a subgradient. Then I have Fy larger than Fx, G1 inner product Yx and larger. Now I multiply everything with lambda. So I have this. And now for this one, I multiply everything with 1 minus lambda. So I have this. Then what? Because I have this, so I add them. Okay, here are important things. It's very important. This kind of thing looks very innocent, but actually many trapped inside. Because this is a set. So this is Minkowski sum. This is not simple addition. This is set plus set, okay? So, but if you look carefully, this one and this one cancel each other. So therefore, in the end, it's just one partial f, okay? Or one subgradient. So that's the idea. And then what? Up to here, everything here is singleton. This is a value, this is a value, this is a value. G is a subgradient, so it's one value of the subdifferential. This is singleton, so all the plus here are normal plus. But this plus is a Minkowski sum, okay? Then what? Then these two add together, the lambda cancel out, so I have a Fy. Larger than this thing, add this thing, so I copy. And then now, this part, I use Janssen. Then this part is above this. Then now I have this thing. And then this thing is what I want. What is this whole expression? This whole expression is f of y larger than f of a new x. This is x, right? F of x plus something y minus x. The definition of subgradient is, I don't care what does it look like. If this thing fit into this and this equation is true, inequality is true, then this is subgradient. Now this is true. Fy larger than fx something y minus x. So this something is a subgradient. That's it. The technical detail is, be careful, this is actually Minkowski sum. Alright? That's it, okay? So now, what? We see that subgradient, as I said, that means subdifferential is a convex set. That means what? All the convex set argument goes to here. For example, I have two subgradients. Their convex combination is also a subgradient. Go back to this. I have this line is a subgradient. This line is also a subgradient. That means this line is a subgradient. Why? Because this basically is half of this one plus half of this one. Yes. And in fact, yes, this is a subgradient. Why? Because this corresponds to the hyperplane of this, which is also a support. Correct? Then, this is not a subgradient. Why? Because this green line is not a convex combination of these two red things. Therefore, this is not. And also, this one is not inside the convex set. This violates the convex set definition. So therefore, this is not a subgradient. Similarly, this is not. Okay? Why? Because convex combination, if you forget, we have this thing, this number, and this number is always larger than 0. So we cannot turn back. We cannot have negative. Negative means an arrow turn back. So this is not a subgradient. Okay? So this is different from hyperplane. What? Hyperplane, you have a line, you have two normal. Because A inner product X, you can always put a negative sign and put a negative sign here, right? But for this, no, we always have going down. The reason is because we always put these coordinate -1. And this makes everything good. Yeah. And then what? This is what? Convex hull of two subgradients. So if you have a bunch of subgradients, convex hull of many of them is also a subgradient. Okay. Now another argument. Because it's a set, is this set closed? Yes. So again, f is convex. I forgot. We only care about convex function. We don't care about non-convex function. So if my function is this, first of all, this line has subgradient. This line has subgradient. But this one, no, because you cannot have a line that under it everywhere. This part you have to cut through it. No. So f is always convex. And then of course I care about x is in domain. If it's outside, we don't care, okay? And then now I have a bunch of subgradient. GK, all of them are subgradient. And then all of them for OK are subgradient. And I have a funny thing, limit this. Then I'm saying this limit is also a subgradient. What I'm talking about here, this is the analytic or calculus explanation. Now let me give picture. This line is a support at this point, right? So this is my G1. Now I slightly go a little bit angle. So now I have this. This is my G2. And then I slightly go angle. Now I have this. I have G3. You see what I'm going to do, right? Then I have G4, G5, G6. So what are these angles? Here, 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 here. In the end, I have this line here. Then I'm saying, if this one is subgradient, this one is subgradient, this one is subgradient, this one is subgradient, blah, 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 blah. In the end, this one is subgradient. And since I'm moving from the largest possible G to the smallest possible G, I travel through the whole set. And if all the limits agree each other, this is definition of closeness, then this set is closed. That's the idea. So, and the proof actually very easy. I have this is convexity, and I have subgradient. And this is true for any GK. Now, what? Because I have limit, GK go to G. Okay, now calculus. That means epsilon delta. For all epsilon, there exists a sufficiently large n such that for any k larger than this, the distance of them is infinitely, not infinitely, I mean arbitrarily close. Right? Then that means this line is for any k, because this is for all k. So this one is equal to k. And then for all k, include this, right? So this thing also apply here. So now I have the same equation. Lastly, I put a limit here. Yeah, I put limit here. This is on k. Limit here on k, nothing on k. I don't write it down. Limit here on this term, nothing on k. I don't write it down. Limit here. Okay, there's a k, so I put it here. So now I have this. Okay, and what is this? So I have this. Now this thing under this. So this thing, what? Fy larger than fx, y minus x, something. Definition of subgradient. This is a subgradient. So therefore, if I have a limit of g converge to some g, and all of them are subgradient, then this is also a subgradient. So what are these? This means we can actually use limit to compute subgradient. Out here are example. Okay, what I showed, let's recap. I just showed that, number one, subgradient is a set. This is a set. So we talk about, is it a convex set? Yes, it's a convex set. Number two, it's a closed set. Number three, here's a 3. It's possible this set is empty. For example, I have a function that is positive infinite everywhere. So what is the picture of subgradient? Subgradient is I have this, and I have a point here, I have a line below it, right? Imagine now this line go to positive infinity, then this line also go to positive infinity. But you cannot have infinity in number because it does not belong to number. So this line actually does not exist. So actually, if I have this funny function, you don't have support. This is a funny function. Of course, you may wonder, who the heck talk about this? This is important because when we talk about indicator function will send things to infinity. Okay. Secondly, what about this? Actually, this also have no what? Subgradient, but at a funny point. So what is this? This is something like this, okay? This is square root x. No, square root, yeah. Anyway, then what? Well, at this point, first of all, you know, at x, when it's slightly negative, we have complex number. So this naturally is a troublemaker. But what's the other issue? What is the definition of subgradient? What does it mean? For all y. Yes, I almost forgot. For all y. That means I have a function. This is on x or y, okay? And now I have a particular x. I fix here. Now I have a straight line. Now I move along this line, but on y, that always my fy is above this straight line. And this is true no matter where I move along this curve, even if I go to here, right? This is an important picture. Why this one have no subgradient? Because I do not have this thing. By definition, this part does not exist. This part is complex analysis. So if I want to build a subgradient, that means I need to build a line that like this. Oh my gosh, what are here? Error. So this one have no. So therefore, this means what? This means naturally we will come to the question, when does subdifferential exist? So let me recap.
Subdifferential is a set. What set? Fy larger than fx plus any g that y minus x for all y. This is all the g. Number two, subdifferential is a convex set because this is a set. And I write this, okay? Number three, subdifferential is a closed set. Okay. Number 4 is existence. The existence is subdifferential of x is never empty set if x is strictly inside the domain of f. And strictly inside the domain of f, mathematically is relative interior of domain of f.
Okay, what the heck is it? Let's explain it. If x is inside RELINT, what the heck? Okay, so some textbook write this as relative interior. I write longer. So what the heck is this? First, finish the reading first, then I explain. If x is in the relative interior of domain f, then this guy exists. Exists means non-empty for convex f. So this is a proof. Okay, so let's look at it. F is convex because convex. Okay, let me use better color. F is convex. So this is because of convex, right? Youngson's inequality. Then what? Now is this part. Let me put it in green. So what is relative interior? So this part have three things important. Okay, what the heck is this thing? F, function f, no problem. So let me do it. This is f. This is domain f. Okay. Now I don't write x anymore. I write dom f. So suppose due to some reason, I just define my f up to here. Okay. Everything outside this region undefined. Okay. Then what is domain f? This part is domain f, right? This is domain f. Okay, which is on a subset of the input set, right? And then what? What's interior of domain f? Let me use green. Means I don't use these 2 points. There's a hole here. So that means this line segment without these 2 points is this, right? Okay. Then what is relative? Relative, let me put it red. Relative is, in one-dimensional case, we don't care this thing. But we always talk about multi-dimension. So when we draw this picture, actually we are drawing, okay, let me now draw 2D. Okay, so you have, okay, forgive my drawing, it's so difficult to draw, but you got the idea, okay? So something like this. So now I have what? I draw it like this. So this is my big X. So F is X to Y, but Y is always R, okay? So this is R, okay? And then in this thing, I have what? I have this, right? This thing is my domain F. What is interior of domain F? So interior of domain F will be this whole thing, but without the line. Without the line, that means it's okay. So this thing is interior of domain of F. Lastly, what the heck is this? Here's the thing. This line, this plane, let me draw it. This plane is a vector space. So it's a space. Then this thing is inside this space because it's a subset. Because this thing is this, right? So every vector space property carried over here. Then what? This thing is also a subspace of this because you remove the outside. So everything here go to here. Now, because this is a vector space, that means we can talk about linear algebra. Something like what? Dimension, rank, that kind of thing. So basically, the relative interior is saying that if this thing is what? Is a rank 2, that means dimension 2, because this is R2. Let's say this is R2, okay? Then this thing have a dimension at most 2. So this is the meaning. This means I'm relative to this. So in other words, what the heck is this? This means regarding to the ambient vector space, if I'm strictly inside the interior of domain F removing the boundary, then convex subgradient always exists. Now go back. So relative interior is interior relative to the linear space spanned by the Rn Euclidean set. So if this is true, that means I have a neighborhood around X in the alpha subspace. That means in the definition of the vector space, that is entirely contained in domain F. So I have this, right? This is my interior domain F. So now I have a point somewhere here. I always have a neighborhood. That means I have a ball. This ball follows all the geometry of the ambient vector space. That means entirely inside this domain. Then what? Then, because F is convex, then there is what? Supporting hyperplane. This exactly is this kind of picture, right? So, in other words, I have a point here. So this point is here. Now go up to 3D. Very difficult to draw, but okay. I have a 3D plane supporting at this point, okay? Right? What's the definition of subgradient? If my function is below a support which is linear, that is this green thing, this green plane, then this is a subgradient. And this green plane is generated by this particular point. This point is strictly what? Inside this black circle, which is called RELINT. So I have just give you a particular hyperplane that below my F. This is what? Subgradient. Therefore, subgradient exists. Okay, done. In other words, as long as we don't touch the boundary, we are happy. This thing have no subgradient because we are talking about boundary. If we are only caring about what? Strictly inside the dom F, we can now talk about subdifferential. That means we always just talk about everything strictly inside the domain, and we are happy. Talking about subdifferential at the boundary is complicated, and lots of people doing research actually on the second bullet point. So that means if I give you a function, and I have a domain, this is a domain, okay? Is there a subgradient here at this particular point? Sometimes yes, sometimes no, and it's difficult to talk about it. But if I'm always in an interior point, always have subgradient, happy. And actually this is also the starting motivation reason why you have this many crazy definitions, including this one and this one. Because you are trying to say, oh, now yes, I'm exactly at a boundary point. So I cannot talk about the existence of subgradient at this particular point. So I have to talk about it using limit. So therefore, you have this. That's the argument, okay? But as I said, no, okay? Good, okay, that's it. I mean, if you do a PhD in this area, then you talk about this, but we don't.